Let's continue to look into other topics. And here in the third section of the chapter 9, Deflection of the beams, we're looking into the statically indeterminate problems. And here are the two typical such problems we're going to illustrate in these sections here. Basically, the statically indeterminate problems can be categorized by, we look at the we look at the two examples. And the first one on this example here on the left hand side, and we can see for this case we know the reactions at this site would be vertical loading, and that's unknown, so let me call this as RA, and also this has the unknown bending moment at point A here. And so basically the two unknowns, or maybe sometimes if you like you can add the horizontal force, let me call this is the FA here. Basically the three unknowns reactions can be determined by the equilibrium equations and the sigma in y direction and the bending moment about any point equal to equilibrated by the whatever the given, say omega divided by 2 L square. Okay, so basically in principle three equilibrium equations are able to solve for three reaction force. And we look at the examples on the right hand side here. Basically here we have, let me change the color here, we have reaction force the same as the left hand side. The left example, this is FA, and this is the bending moment and A here. In addition, here at the support we expecting the force, reaction force RB. So basically here you're expecting there's a 4 sorry, here is a little bit. So basically here we're expecting there's a 4 unknowns, 1, 2, 3, and 4. And however, we only have 3 equilibrium equations, and like we're showing here or here. So 4 unknowns with 3 equilibrium equations, basically this, per our understanding, this is a typical static indeterminate problems. Okay, so here we need to come up with one additional, so we need one more equations allow us to solve for the 4 unknowns, and such one more equations from here for deflection of beam, basically that is coming from the equations of deflection. So from the equation of deflection we will be able to get more information from geometry. Okay, so that is the hint, that kind of the steps of the solution process. So here we can look into more the examples here, the illustration here. So basically the one additional equation basically is solved for is by something. Okay, so basically here we need one more equations and for 4 unknowns, and that equation coming from this is the deflection equation here. Okay, so from the deflection equation we simply apply is once we solve the deflection equations we can get the metric informations. So we see how these things can be done. So we continue to look at this example in specific in details here, and step 1 in solving this problem is to get a free body diagram, and to analyze all the reaction forces. And here we have 4, and 1 force, and 2, and 3, and 4. Okay, so here we have in total 4 unknown reactions, and here we have utilized 3 static equilibrium equations here. So here we come up with one more equation that basically is based upon the equation of the deflection. So we start from here. Okay, start from here, and from the earlier exercise, and what we have learned, and basically is here we need to first to get the moment. Okay, so to get a moment, and you have two ways you can try, and here illustrated is using the free body diagram. And the free body diagram, simply let me be more specific which portions. So basically, if you pick this portion here, and the distance of that portion basically is x, so this is the free body diagram you pick, and that is a free body diagram and coming here. So in this free body diagram, and you have basically the free body diagram is this portion here. Okay, and here from here we copy the 1, 2, 3 forces here, and then also from these sections, and we expecting the V and M, that direction here, and on the top we have the distributed loading here. Okay, so using this free body diagram, you should be able to quickly come up with this is M as a function of X equal to this one. So once you have this one, you plug in here, and then you begin to solve for, and keep this in mind. In this formulated the bending, you have included two such symbols, and that symbols simply is coming from this and coming from that, and those are part of the unknowns. At this moment, don't worry, you simply proceed your calculation in terms of those symbols here. Again, that is the one, although we don't know its value yet, but we continue our integration in terms of those symbols. Okay, so you integrate one more time. So basically here for this one, you integrate one more time, you got this one. And here again, this one is our slope, and usually you can interchange with theta. Okay, so that's the reason, and this is what we call the slope equations. Again, you can refer to the previous, the section 1 or section 2. So we integrate. So this one, the right hand side is the integrations of this equation with respect to x, and we come up with the integration constant C1. And then based upon this, we integrate one more time, and so we integrate this one more time, we get this one, and this is called the deflection equations. Okay, and the right hand side is the integrations of such equations, and then you come up with additional one more integration constant. So right now you have two integration constants, and that integration constant is the additional two unknowns coming up from the integration of the differential equations. And again, right now strategy is we try to solve for the two unknowns, so we apply the boundary conditions here. And here we have two boundary conditions, and maybe the here you can apply for is a boundary condition at A here. Okay, so at x equal to 0, that means at point A. And we know from here the deflection equal to 0 and slope equal to 0. So using the two equations, you can solve for C1 and C2. Okay, and then in this case, the you have the deflection equations like this. And again, at this moment, the AY and MY still the symbol that been propagated from the very beginning of this solving equation here. Okay, and then you can continue to apply the additional equations, the boundary condition here. So we have utilized the boundary condition here. Now we're going to utilize the boundary condition at B here. Okay, so at S equal to L, that means at the point B. So that is another boundary condition. This is the key step, and that allow you to formulate in addition to the three equilibrium equations, that allow you to provide one more equation. And we'll look at how this works. So at point B, we know the deflection equal to 0 because that is support, so no deflection here. So based upon these equations, you apply this boundary condition. So this equation simply becomes this. Okay. So this is the additional equation. Let me write it up here. 0 equal to minus 124 omega L to the fourth plus 16ay and L3 minus 1/2 ma L squared. So basically with the 4 equations and how many unknowns? 1, 2, 3, and 4 unknowns. In theory, you should be able to solve for these the algebraic equations. Then from there, you should be able to find the ax equal to 0 and ay, ma, and b equal to such a case. And solving for these 4 equations, that would take a little bit of time. But in theory, you should be able to do it. And I think all the high school students should be able to do this one here. Okay. So basically that is the case, and let me review the important steps here. Step 1 is the equilibrium equations, and then this is a step 2. We start from formulation of the equilibrium equations, in which the little bit rigorous will be spending to formulate the m of x such that we can solve for these equations. Then step 3, we begin to apply the appropriate boundary condition here. And here we have the strategy is we first adopt the boundary condition at A and to solve for C1, C2. Okay, and so C1, C2 when solved for, then you apply the remaining available boundary conditions at B here, and then to formulate the additional equation here. Okay, so basically here let me formulate. Here, let me try to find out what the available boundary conditions here available to us. So the first one is at x equal to 0, y equal to 0 deflection. The second one is at x equal to 0, the slope equal to 0. Basically, that is describing the condition at A here. The third one is at x equal to L and y equal to 0. This is the third one describing the boundary condition here. Okay, so now again we look at the step 3. Step 3 is to apply the boundary conditions to solve for C1 and C2. So here for this case we have applied the 2 conditions in step 3, and then step 4 here is to apply the remaining, and that is we apply this one in step 4. Okay, so here I want to make a comment, and you may ask me, hey, can I in step 3, okay, can I in step 3 to apply these equations and these boundary conditions in step 3? So right now let me use this label here. Okay, so can I apply the 2 boundary conditions in step 3 to solve for C1 and C2, and then in step 4 let me apply these conditions in step 4? And the answer is yes. The answer is yes. Okay, and again the answer is yes. Out of the 3 boundary conditions, you can pick whatever you like in step 3. You can pick 2, okay, pick 2 and whatever you like, and to solve for C1 and C2, and then you pick up the remaining one and for in step 4. Okay, so basically this kind of selections is arbitrary. As long as you keep your calculations correct, then your answer should be the same as the other people which adopt the different boundary conditions for step 3 and for step 4. This is the very important concept here, and most of the time the textbooks, the instructors didn't explain this well. But here I want to tell you, and out of the available boundary conditions, you can pick the preference. Based upon your preference, you can pick whatever you like and solving for and coming up the additional equations. If you don't believe this, you can try the different scenario of picking up, and based upon my selection here, you can give a try. Okay, and actually I encourage you to try it as the first time learners, and in a way to reinforce such a concept and such the I would say arbitrary selections of the boundary conditions for step 3 and for step 4. How come this works? The reason why is based upon we call the linearity, And all the situations we're dealing with here and so far in fundamental mechanics material are in elastic regime, and which means in the elastic solid mechanics, and most of the situation can be formulated in mathematics in linear equations, in linear differential equations, or in linear algebraic equations, because of such a linearity, and that allow the students, and in such case to pick up the any arbitrary two boundary conditions for step 3 and remaining boundary condition for step 4. Okay, so keep this in mind. Then we look at the second example here. In this example, basically is we have the different the clamp site here. So the step 1, we using the free body diagram to find out the reaction force, and at A the same as before, and at B, because this is a clamp site, we, in addition to the reaction force, we expecting reaction moment. So here for this case we have in total 5 unknown reactions, and then 3 equilibrium equations. Okay, so here we formulate the equilibrium equations in x direction. So ay equal to this one equal to 0. So this one is kind of the trivial. Then here for the second and the third equation we have this one. So right now here we have 5 unknowns, so we need 2 more equations, okay, to solve for the 5 unknowns. And the 2 more equation basically is coming from the step the deflection equation here. Okay, so again the boundary conditions is this. We start from the formulate this one, because here for this case this is the static equal distributed loading case. So we start with this one will be easier, and that will allow us to kind of avoiding the very little bit complicated kind of free body diagram and that kind of things. Okay, so I pick this one. So starting from here, we integrate once, then we have this come up with the first integration constant, then we integrate one more time, then that one will come up with the second integration constant, and then one more time, then third one up here, and one more time the here up here. So in total we have 4 integration constants. And such integration constants, and that can be solved for, is this. And the first one we can look at is the boundary conditions here, and we can try to utilize, and like I said, here you can see I have formulated the things here. Okay, so basically here we apply the 1, 2, 3, 4 boundary conditions, and that basically formulated here and allow us to solve for C1 and C2. Okay, so for this case we see and we completely have the C1, C2 solved for, and C3, C4. So let me dig out this one. This is equal to 0, this is equal to 0, and C1 and equal to here, and C2 equal to here. So for this case, the deflections of equation is totally to this moment, this totally solved. So this is no equation here. So from this case we plug in, and here I want to get 2 more equations. 2 more equations basically for this case is this. I try to adopt this equation. This equation is called the EIY double prompt. So here, if you remember, so let me change the color here. This is called the deflection equation. This is called the slope equations. This is called the moment, bending moment equation, and this one is called the shear force equations. Okay, so we start from here. This equation provides us the moment, the information about the moment. So let me write it up. EIY double prompt equal to minus omega 2 square plus C1. C1, let me plug in here, omega 2 L at, and then C2 is this one, minus omega L square and 3. Okay, so this is about the moment. So from here, I want to solve for is this MA. So MA is the moment at x equal to 0. So therefore, here we EIY double prime and equal to, let me do this one more carefully. EIY double prime at x equal to 0, and basically this one will give us is the this is the moment equation. So this basically m of x. Okay, because here we know the the y double prime equal to the EI and m of x. So basically here EI y double prime equal to m of x here. So this one is basically mx. Okay, so basically this is the MA. Okay, on the other side, when we plug in the whole equation when setting up x equal to 0, basically that is minus L squared over 3. Okay, so this number is simply obtained by using this equation with x equal to 0. Okay, so that's summarized here. And in a similar way, and MB and equal to is the moment. This is a moment, and MB is happen at x equal to L. So again, using these equations with x equal to L, then you should be able to determine MB equal to this one. Okay, as summarized here. Okay, so with the two pieces of the two more equations, basically is solved here. Okay, so you solve for this one. Basically here you already have this one be determined. Then using the three remaining, you should be able to solve for AY and B and AX. Okay, so in this case, this is totally solved. And for this case, you can see that's a little bit different kind of the thinking process than the previous example. And if needed, you can rewatch and this portion here.